bom dia a todos. É um prazer recebê-los aqui para a abertura dessa semana da Sociologia do Conhecimento. Eu dou bem-vindo a todos pela UFMG, pela Escola de Engenharia, pelo Instituto de Estudos Avançados Transdisciplinares, o qual eu tenho a honra de presidir. Desejo boas-vindas ao professor Harry Collins, professor Paulo, por essa interação com nossos pesquisadores aqui na UFMG. Rapidamente, a vida do professor Harry Collins é patrocinada pela Cátedra de Ciências da Natureza e Tecnologias do Instituto de Estudos Avançados Transdisciplinares, o IEAT, e pela FUNDEP, patrocina essa cátedra. O IEAT tem 5 cátedras: Ciências da Natureza e Tecnologias, essa, Humanidades, Letras e Artes, Ciências da Vida, Criminalidade, Violência e Políticas Públicas, essa última patrocinada pela Fundação Ford, as outras 3 pela FUNDEP, e a gente está abrindo agora, em processo de consolidação, a cátedra sobre estudos ibero-latino-americanos. Já trouxe a professora Beatriz Salo e trará no segundo semestre o professor Júlio Ramos. Estão abertas as inscrições para as cátedras de 2009, novembro de 2008 até novembro de 2009. Então já estão abertas inscrições para essas cátedras, eu convido a todos. O IEAT é um instituto recente, ele foi institucionalizado em 2005, depois de funcionar 5 anos em regime provisório. Ele tem como objetivo a difusão da cultura transdisciplinar e a prospecção do que é o avançado nas várias áreas de conhecimento. O que distingue o nosso instituto de outros congêneres no Brasil é de que a transdisciplinaridade, para nós, ela está ancorada no conhecimento disciplinar. E a gente entende que só na medida em que há uma certa profundidade no conhecimento dos campos disciplinares é que eu encontro lá no fundo desses conhecimentos, seja das ciências, da filosofia, das humanidades, as porosidades, os desafios, os limites que obrigam esse campo do conhecimento a conectar-se com outros. Então essa é a proposta do IEAT. A transdisciplinaridade se alimenta do conhecimento disciplinar e não propriamente vai contra ele. Além desse programa de casas, o IEAT tem o programa de professor residentes, são professores da UFMG que ficam 1 ano desenvolvendo pesquisas em caráter de ponta e também transdisciplinares, cujo edital vai ser aberto para o segundo semestre para 4 vagas. Temos também o programa Grupo de Pesquisa, o programa de conferências nacionais, internacionais, o programa de visitas nacionais e internacionais que o IEAT desenvolve. A próxima atividade do nosso Instituto será os encontros transdisciplinares, outro programa do nosso Instituto, que esse ano está versando sobre a questão das novas mídias de comunicação. O próximo encontro trans será na Escola de Belas Artes, no dia 13 de maio. São encontros mensais, já fizemos 2, faremos esse dia 3 de maio, depois fazemos um outro em junho. Eu gostaria de agradecer o comitê diretor do IEAT, que me ajuda na direção do Instituto, o professor João Antônio de Paula, Maurício Loureiro, da Escola de Música, João Antônio de Paula, da Faculdade de Ciências Econômicas, Sérgio Pena, do Instituto de Ciências Biológicas, e o professor Eduardo Mortimer, da Faculdade de Educação. Agradeço também o Comitê Científico do IEAT, que é composto de gente do Brasil inteiro, que é o responsável por ter selecionado o professor Harry Collins para a vinda à nossa UFMG. E agradeço especialmente o professor Rodrigo, que é o anfitrião do professor Collins, que propôs o nome do professor para ocupar essa cátedra nesse período. Então, desejo a todos uma boa conferência, agradeço especialmente a equipe do IEAT, os funcionários, os estagiários que me ajudam na realização dessas atividades. Passo a palavra ao professor Rodrigo para a condução dos trabalhos.
Bom dia a todos. Gostaria inicialmente de dar boas-vindas ao professor Harry Collins, Rob Evans, pela sua disponibilidade e boa vontade de virem. Nós estamos todos aqui para escutá-los. Gostaria de dar boas-vindas a todos vocês, por estarem aqui presentes, terem vindo. A maioria das pessoas que se inscreveram são professores, pesquisadores, alunos de pós-graduação. Então nós temos um público aqui que é formador de opinião, e isso é muito importante, dados os objetivos desse evento. A vinda dos professores faz parte de um projeto maior, que é a divulgação, disseminação dessa área no Brasil, que ainda é feita em poucos lugares. E nós temos então estamos atuando em 3 pontos para essa divulgação. Um deles, esse acordo que foi fechado entre o Departamento de Engenharia de Produção da UFMG e a Universidade de Cardiff, onde consta que todo maio virão professores da Universidade de Cardiff, sempre o professor Harry Collins ou o Wal Evans, ou os dois, e professores da UFMG vão para a Universidade de Cardiff em agosto. Então nós vamos ter esse intercâmbio até dezembro de 2011. Parte disso nós teremos eventos, esse é o primeiro deles, o outro será em 2010, nós vamos preparar com mais tempo, E nós também estamos fazendo um esforço grande de trazer publicações específicas dessa área para o Brasil por meio de tradução de livros específicos. Queria tomar liberdade só de mostrar alguns que a gente já está preparando para o lançamento. Isso é uma organização, é uma coleção que está sendo organizada por mim e pelo professor Francisco Lima, do Departamento de Engenharia de Produção, em conjunto com a editora Fabrefacto. A ideia é uma coleção internacional, a gente quer chegar até 14, 15 livros, e nós vamos começar, então, com 2 livros sobre controvérsias na área de tecnologia e na área de medicina. Isso faz parte, são exemplos do que o professor Collins vai falar sobre a primeira onda, da segunda onda de estudos da ciência, onde ele vai explicar bem essa segunda onda. Então esses são exemplos dessa segunda onda. Depois nós vamos ver a questão da modificação, como que o conhecimento é alterado, transformado no livro Invertendo a Ordem. E agora, como exemplo da terceira onda, é o livro Repensando a Expertise, que foi publicado esse ano, e a gente vai estar trazendo todas essas edições a partir, até o final do ano que vem, todos esses livros vão estar à disposição. E por fim, tem 2 exemplares aí de uma área muito interessante dentro da Sociologia do Conhecimento Científico e Tecnológico, que é a discussão sobre a interação homem-máquina, limites de sistemas especialistas, limites e possibilidades, onde o professor Harry Collins tem 2 livros publicados nessa área. Também nós vamos trazer esses livros para o Brasil. Então, isso aí faz parte desse esforço maior de tentar disseminar e difundir esses trabalhos que são feitos lá na Universidade de Cardiff e também com outros autores de fora, e que são livros, vamos dizer, de extrema aceitação internacional, e que a gente selecionou para poder iniciar esse intercâmbio entre áreas de conhecimento. Bem, por fim, eu queria fazer alguns agradecimentos. Sempre fica assim, poxa, lá vem os agradecimentos, mas esse foi um evento feito com poucos recursos, A gente começou a preparar o evento em fevereiro, mas a ideia era tentar disseminar o máximo. Tinha 220 inscritos, mas eu acho que devido ao jogo de ontem o pessoal acordou mais tarde, Então eu queria agradecer muito ao IEAT, na figura do professor, que é seu presidente, o professor Carlos, por ter financiado a vinda do professor Collins e dar todo o apoio institucional. ao Departamento de Engenharia de Produção, que deu apoio institucional e financeiro para a realização do evento, ao CDCOM, que é o Centro de Comunicação da UFMG, eles fizeram a parte toda de assessoria de imprensa, marketing e a parte do site, né, do evento, que foi o maior meio de divulgação que a gente teve do evento, né? O pessoal do CAC, que está preparando toda essa estrutura que a gente está utilizando aqui, queria fazer um agradecimento a vocês. Diretoria de Relações Internacionais, que é o guarda-chuva, né, que a gente utiliza nessa relação com a Universidade de Cardiff, a Escola de Engenharia, obviamente, né, e a FUNDEP, em conjunto com a IEAT, está financiando. E queria agradecer muito aos meus alunos que me auxiliaram na organização desse evento, né, Fernanda, Mariana, Rodrigo, Raquel, Lucas. Queria agradecer muito, porque foi um apoio voluntário, né, que eles fizeram e foi muito trabalho. Tá bom? Eu espero que vocês aproveitem bastante o evento.
It's a great pleasure to be here. Thank you very much for all those who helped to organise this and helped to fund it. My first time in South America, and it is enormously pleasant. I must say a special thanks to Rodrigo Ribeiro. I don't know how many of you know Rodrigo Ribeiro. Let me tell you something about Rodrigo. He came to Cardiff to work with us for 4 years. He is probably the most energetic person I've ever met in my whole life. And after only 4 years, we now work for him. That is why, he ordered me to come. So now, I suppose I should start to talk about, to give the talk I prepared. It's about the nature of science and the sociological analysis of science. For a sociologist, or anyone with a sociological conscience, there is enormous terror in the world. We are always worried about what I will call the eternal problem. We always suffer from terrible angst, terrible anxiety. And this is the first part of a sociologist's education, is to learn to be terrified and learn to be anxious. Why? Because how do we know whether what I believe, how do I know whether what I believe is true? Because the first thing you learn as a sociologist, when you encounter the sociology of knowledge, is what you take to be knowledge is just an accident. It depends where you were born and brought up. So it's the same as your language. It is an accident that I speak English. That is where I was born and brought up. My religion is an accident. If I was born and brought up somewhere else, I would have a different religion. And yet I believe, or at least when I was a child, I used to believe this religion with absolute intensity and would even kill people to defend it. And then you say, hey, then you learn the sociology of knowledge, and you discover, well, maybe this thing that you want to kill people for is just pure chance, not really a true belief. So the sociologist of knowledge is always terrified and always looking for some way to escape from this anxiety. Always trying to escape from the possibility that we are merely trapped in the social collectivities that provide our beliefs and our ethical codes, and that if we lived somewhere else, we would believe something completely different, but with equal intensity. This is a picture that the sociologist has of a human being, a little insignificant stick figure, a little insignificant drawing in the middle, who is formed entirely by the social groups in which they are embedded. These social groups are represented by these blobs. Here is one social group, maybe this is English-speaking people. Here is another social group, maybe this is people who play a lot of sport. Here is another social group, maybe this is a religious person, religious people. You sit and you sit in these blobs of different communities, and this makes you. That is all you are, just those blobs. But science is Science promises an escape from this anxiety because you can reach out and touch something outside of the social collectivity that form you. Touch something which is absolute truth, which is the same for everybody, whichever collectivity they sit in. And that's why the sociologist of knowledge is so interested in science. Is this a way to escape from anxiety? Well, now let me tell you about the study of science from a sociological point of view as it has taken place over the years. And I divided up, Rob Evans and I wrote a paper in 2002 in which we divided up the study of science into 3 waves, as we call it. Wave 1, you can say, ran from about the 1940s to the 1960s. That maybe the starting point was earlier, but it doesn't matter. And in this, science is just as I've described it in the previous slide, the most secure form of knowledge. And the questions for wave 1 was, what sort of society can we arrange that will produce and nurture this most secure form of knowledge? Wave 2 began from the late 1960s and has run really up till now among sociologists, among people who study science from the point of view of the social sciences. And this is nearly all my work has been done in what we call wave 2. And this starts to look at science as something more like other kinds of knowledge, not something that can create this escape from uncertainty and terror. And most of my talk I'm going to explain why it is that maybe science isn't as secure an escape from this terrible dilemma as we thought. That is what I've been doing for 3-4 decades of my life, trying to explain this. And then more recently, from the early 2000s onwards, wave 3, where we say, well, okay, we've done all this damage under wave 2 to the notion of a science, an external or universal science. But if we're going to preserve our society, the society we like to live in, then somehow or other we have to rescue science. We have to make sense of the fact that science isn't just ordinary knowledge, there's something special about it. And the question for wave 3 is, how can you do this? How can you make philosophical sense of this, given everything that was done under wave 2? First of all, let me talk briefly about wave 1. Wave 1 was happening when I was growing up as a child in the 1950s. And in Britain, for years, you could never listen to the news or open a newspaper without seeing some discussion of Calder Hall, which was the first commercial nuclear power station in the world. And we were told continually how wonderful science was because Calder Hall was being built, and how this was symbolic of the wonderful future, the wonderful thing that science could do. Lewis L. Strauss, an American, speaking in 1954 for the National Association of Science Writers, looked forward to a time when our children will enjoy in their homes electrical energy that is too cheap to meter. This is what science brought about, all post the Second World War. And that was the image of the scientist, the man, it's mostly a man, in a white coat, speaking with authority about almost everything. What is this canonical view of science? Science reaches towards certainty via theories, via observation, and via experiments. Here are scientists doing theories, observing, experiments, trying to reach a conclusion, and eventually they reach a conclusion. P is the truth. And then this is fed to the public, and the public accepts that P is the truth. They all believe P as well. This is the wave 1 model of science. Authority from the top down. And the sociology of science, which was associated with wave 1, was really also largely associated with Robert Merton, the American sociologist from Columbia, who said that in order to have a society organized to produce science of this type, you needed a set of norms, which he called kudos, and those are the set of norms. Communalism entails that scientific results are the common property of the entire scientific community.
Universalism means that all scientists can contribute to science regardless of race, nationality, culture or gender. Disinterestedness, according to which scientists should not present their results in tandem with their personal beliefs or activism for a cause. Scientists should have an arm's-length attitude towards their findings. Originality, claims by researchers must be novel and add something to our knowledge and understanding. Skepticism. Scientific skepticism means that scientific claims must be exposed to critical scrutiny before being accepted. And these were the norms of science, and this is what informed the sociology of science up till the 1960s. But there was always some problems. Theories, they're not really thought to be too satisfactory on their own. They need experimental verification. Einstein was one of the few people who claimed that a theory could sometimes stand up against a negative experimental result. But most people thought, no, you need the experiments to back up a theory. And the more we learn about theories, the more we know that they're not so secure. So my colleague Trevor Pinch wrote a very interesting paper about John von Neumann, who, all way back in the 1940s, proved that, if anybody knows this, that you could never have a hidden variables theory of the quantum realm. That the quantum realm is essentially random, and you could never have any underlying causality to it. And this was believed for decades. Anyway, it turns out it's simply a mistake in von Neumann's paper. He just made a mistake. Nowadays you have all kinds of arguments about modern theory, string theory. Some of you may have heard of Alan Sokal, who published a hoax paper in the Sociology of Science, which was widely publicised. Just a little after, two brothers called the Bogdanovs published several papers on string theory in the scientific journals. This is even more embarrassing, because nobody knows whether these Bogdanov papers are a hoax or not. Maybe they are, maybe they're not. B. Smolin and various other people have been writing recently about string theory and saying that the social organisation of string theory is such as to keep out other competitors to such an extent that it is ceasing to act. Scientists doing string theory are ceasing to act according to the norms of science. Donald Mackenzie has written a wonderful book about the nature of mathematical proofs using computers. There's this terrific argument about whether a proof is really a proof if a computer can prove it, or if a computer can prove it. It's only been shown by a computer, and computers have bugs. Do you need a human being to do the proof? Or wait a minute, is it because humans are fallible that you can't trust a proof done by a human and can only trust a computer by a proof done by a computer? This goes round and round. And my colleague, Dan Kennefick, has done a case study of the analysis of the theory of inspiring binary neutron stars, what happens to neutron stars as they circle into each other, and shows the way that that theoretical argument could not be settled just by theoretical work. Under wave one, this is the typical problem for philosophers concerned how theory is articulated with facts, how facts join up with theories. Facts and findings under wave one were normally taken as fixed or given by observation and experiment. But though towards the end of this period there was still concern for the theory-latedness of observation, as Popper called it, this concern began to grow. It's easy to see the problem with observation. We can do an experiment now. Let's take this picture. Hands up those who can see a face in this picture. I think you won't know this, but that's me, everyone. Hands up those who can't see. Good. So I'll explain what the face is. Here's the face. Here is the face. It is a face that we would say looks like Che Guevara, with a beard here. Here is the left eye. Here is the right eye. Here is the nose. Here is the chin, here is the right cheek, this is a highlight, the light is shining this way. So now I've explained to you how to see. Now those people who put up their hands and said they couldn't see the face, put up their hands if they now can see the face. One person you see. You see the problem with observation. Two people. You see the problem with observation. It's when you can't see this, Even when it's explained, you still can't see it. So observation is not such an obvious thing. And then think about it. All those people who could see the face, you think you're really seeing a face? You're not seeing a face. Take another look. It's only black and white patterns. Why do you think you see a face? Look at the amount of work you are doing when you put up your hand and say you've seen a face. There is no face there. Actually, this is a photograph of some mountains in China. So here's a little problem with observation. It's not so clear what observation means. Put it another way, even if those who still want to think you've seen a face, remember if you've been brought up in, say, American Indian society where people don't grow hair on their faces, you would never see this as a face. Or if you weren't used to seeing photographs where black and white images are transformed into three-dimensional coloured objects, you would also never see it as a face. So this is what I meant by saying observation is theory-based. More profound movement, the thing that really began to change things from wave one, was to start to see science and everything else as a set of practices set in forms of life. To start to see observation as actually part of what one does as a social being. And these three books on the left are very important in this change. I put the fourth book, this one here, on the right. I put it in because that's where I learned everything I know from. Everything I ever know is in this little book, which I happened to chance to read in 1967. And only through reading this did I come to read this, and then come to understand this, and then much later came to understand this. These books, this is the book that everybody knows, Thomas S. Kuhn's The Structure of Scientific Evolution, written in 1962. This book here, Genesis and Development of a Scientific Fact, was actually written in 1935 and says nearly everything which is in this book. But it was published in German before the Second World War and is very little known and wasn't translated into English until 1976, I don't think, something like that, when people began to pick it up. But if you read Thomas Kuhn's book, you will see that this book is acknowledged in Thomas Kuhn's preface. And nearly every idea in here is in here, except for the idea of a paradigm revolution. This book is absolutely terrific. In many ways, this book is said to be an esoteric philosopher, and for a sociologist not so easy to approach, but I learned to approach it from this man, Peter Winch, his little book, which I think is fantastic. And this story, this whole story represented by these three books, is how any scientific experiment or piece of theorization or something of this sort has to be understood as belonging in a whole social context. So in Kuhn's case, he called these social context paradigms. Later on, he made a mistake in the second edition of his book and said, oh, I did that wrong. I should have separated out the notion of an experiment as a paradigm and the notion of a culture as part of the paradigm. But no, he should not have separated it out. It needs to be kept all together, these things, as Wittgenstein does. Read Wittgenstein and then read Kuhn. You can see Kuhn as an application of Wittgenstein to science. What does it mean? Practices and concepts are but two sides of the same coin. What you practice, what you do, tells you what to think, and what you think tells you how to practice. Let me give you the concrete example which I got from Winch's book. And this is the idea of a germ. Imagine operations in operating theatres before anybody had the idea of germ. People went in with dirty waistcoats and unclean knives and so forth, and cut people up and they died of septicemia. Then you have the idea of germ, and now if you watch an operation, television, you see there is this ritual where the surgeons scrub their hands like this. Scrub, 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 scrub. A strange ritual where they put the gloves on without touching the outside. Maybe the nurse puts the gloves on for them so they don't have to touch anything. And scrubbing for a long, long, long time. What are these surgeons doing when they're scrubbing? Do you think they're removing germs from their fingernails? Scrubbing the germs away? No. They're making germs. Because the more you scrub, the more you see this surgeon scrub, the more you understand the idea of germ. So this is not to scrub away germs, this is to create germs. With no scrubbing, there are no germs. Doesn't make sense, the idea of germs, unless there's all this scrubbing. You see? So this is like the Kuhn idea of paradigm, more deeply put here with Wittgenstein, and Winch, who has this beautiful example. 1958, long before Kuhn was published. You know, you are making the germs here through your actions. Through your actions, you are learning how to think. You are learning how to conceive of the germ. You know, you scrub so long because the germ, you know, is very small, very hard to get rid of, sticks to you. So this is how the germ is made. You can see it's like the Kuhnian idea of paradigms, made up of concepts and corresponding. Experiment now, which I'm going to run through, the Michelson-Morley experiment, which anybody who has ever done any physics will know about. It was done in 1887. Those are the Michelson-Morley, that's Albert Michelson, that's Edward Morley. And this account is just taken from our book, Collins and Pinch, The Golem, which Rodrigo has mentioned and is translating. This is a picture of the Michelson-Morley apparatus. This is a large block of sandstone floating on a trough of mercury, and on top of it is an interferometer. An interferometer is a device with two arms at right angles. You shine light along the two arms, it bounces back to the mirrors at the end, comes and recombines in the centre, and by looking at the pattern of the light you can tell if with the length of one arm it changes in respect of the other arm, because if it does the pattern will change. This sandstone slab turn slowly on its trough of mercury. And what they were looking for were changes in the length of one of this arm compared to the other arm, changes as the Earth circulated in its orbit around the Sun. Because what they thought, what people thought then, was that light was transmitted through a medium called the ether, and because the Earth was travelling around because the Earth was travelling around the Sun in its orbit, then the Earth was travelling through the ether. The Earth travels around the Sun at about 30 kilometres a second. And therefore what you should have is an ether wind, like the wind blowing through your hair. You should see the wind of the ether coming through this apparatus. And it would mean that apparently the speed of light would be different depending on whether the arm of the interferometer was pointing into the wind or pointing across the wind. And so you should be able to see some changes in the pattern as the interferometer turned in its trough of mercury. There was a complication because the Earth itself is circulating at around that speed. And so this meant that to do the experiment properly, they had to do the experiment at different times of the day. Well, as you probably know, this experiment was done, the best version of it was done in 1887. And they found they couldn't see any difference. They could not detect the speed of the Earth through the ether wind. And any of you who've done physics will almost certainly have learned about this experiment and will know that it is one of the important experimental verifications of Einstein's special theory, which includes the idea that the velocity of light is a constant. But the Michelson-Morley experiment was actually never finished. You see, there is the Earth travelling around the Sun at 30 kilometers a second. But what you don't know is whether the Sun and the Earth together, the whole solar system, is travelling through the ether itself. Maybe it's going in the other direction at 30 kilometers a second. In which case, the apparent velocity of the Earth will be no kilometers a second, 0. If this just cancels out the speed of this. So in order to make sure that's not the case, you need to do the experiment at different times of the year. You need to do it not only when the Earth is up here, but also when it's here, and when it's here, and when it's here. So when it's here, if this is the correct situation, with this whole solar system being translated across the sky, you should see 60 kilometers a second. And here you will see the 30, and here you will see the 30. And here you will still see 0. So to do the experiment properly, to prove that there is really no effect of the Earth's passage through the ether, you need to do the experiment at 4 different times of the year. Furthermore, there is a problem. Maybe the ether is trapped in the building where you are doing the experiment. These experiments are very, very difficult, so they were always done in the basement of buildings. Maybe the ether wind just blows around where the experiment is, so you wouldn't see any effect even if there was one. To get rid of that possibility, you need to do the experiment in a very light building, or maybe take it up in a balloon, so that it's not there. Or there's also the problem that the Earth, you forgive my bad drawing, has mountains on it. Maybe the ether is stuck in little ether wells and in these valleys. And that's why you can't see any movement. To do it properly, you really need to do it on top of a high mountain, or as I said, take it up in a balloon. So you should do the experiment at a high elevation. But none of these are ever done. Well, no, they weren't done until a lot later, in 1887. So that's the story. The Michelson-Morley experiment was never completed. What happened is, of course, Michelson and Morley didn't have any idea that they were doing an experiment which had relevance with the theory of relativity, because the theory of relativity hadn't yet been invented. Einstein's paper was in 1905. So they didn't bother to do the other things because basically their experiment hadn't worked. They were trying to measure the velocity of the Earth. They hadn't managed to do it. Or, a more recent account, which will be published soon, suggests that actually Michelson's main interest was in using the interferometer as a precision instrument, and he wanted to demonstrate how good it was with this experiment. And he failed to demonstrate how good it was with this experiment. So they gave it up. They didn't do what they needed to do to confirm Einstein's theory. No test at different times of the year, no light building, no high elevation. Nevertheless, read any history and you'll see that Einstein's 1905 paper is read backwards to attribute to the 1887 experiment proof of the constancy of the velocity of light. This is how the history is read backwards. And that's the case even though the Michelson-Morley experiment had not proved a null result. And in fact what happened was this. In September 1924, Miller, another person who was doing interferometry experiments, did a better experiment and did find a small positive effect of the ether wind. Not as big as they expected it to be, but they did find an effect. And it was about a tenth of what was expected, but Miller wrote up, the effects were shown to be real and systematic, beyond any further question. In 1925, Miller was actually awarded the American Association for the Advancement of Science Physics Prize for finding an ether drift. Now, Michelson did more experiments to try and prove, because now they knew they needed a null result, so Michelson was interested in trying to prove the null result with new experiments, and they continued to battle and argue with one another. This is what Miller said in the sort of summary paper that he wrote in 1933, 46 years on from the famous 1887 Michelson-Morley experiment. In 3 of the 4 negative experiments, that's experiments which didn't find any ether drift, the interferometers have been enclosed in heavy sealed metal housings and also have been located in basement rooms in the interior of heavy buildings and below the level of the ground. In the experiment of Pickard and Style, where an interferometer was carried aloft in a balloon, a metal vacuum chamber alone was used, and he thought metal would trap the ether. If the question of an entrained ether, a trapped ether, is involved in the investigation, it would seem that such massive and opaque shielding is not justifiable. The experiment is designed to detect a very minute effect on the velocity of light to be impressed upon the light through the ether itself, and it would seem to be essential that there should be the least possible obstruction between the free ether and the light path in the interferometer. In none of these other experiments have the observations been of such extent and of such continuity as to determine the exact nature of the rotation of the Earth and seasonal variation on the effect. Here's his paper, Reviews of Modern Physics, number 5 in 1933, and he says that if you take all this into account and look at his own results, he definitely proved the existence of an effect on the speed of light, and therefore that the speed of light was not a constant. And in fact, right up to 1963, people were trying to demonstrate that Michelson and Morley had been right with experiments using masers. And these were such difficult experiments, it wasn't until quite recent times that experimental proof was absolutely established. Nevertheless, we did a survey of 26 textbooks, physics textbooks in the University Library. We found that 9 of them report or imply that the original experiment was repeated by Michelson and Morley 6 months later or at other times of the year. This simply is not true, but this is what the textbooks say. 6 said quite categorically that no positive ether drifts were ever found. This is not true. Miller found positive ether drift. 1 says that the Miller result was not statistically significant. That isn't true at all. 2 of them give far too much weight to the result in terms of its importance in the proof of relativity to the Michelson-Morley experiment. So of 26 textbooks that we looked at, 16 were wrong on matters of fact and 2 were wrong on matters of emphasis. But this is what the physics student learned about the Michelson-Morley experiment, that an experiment of 1887 demonstrated was an experimental proof of a paper of 1905. And that furthermore, and this is the important thing, that the experiment of 1887, how much time did it take? Virtually none. The experiment was done on a couple of nights of the year, and that was the end of it, the result was found. And the whole history of nearly 50 years of argument about the meaning of that experiment disappears for the physics student and for the general audience. There were lots of other books that we found that gave lots of misplaced emphasis by mentioning the Michelson-Morley experiment and no other experiments. Now the funny thing is, not every scientist who writes a textbook gets it wrong. In 1967, Herman Bondi wrote that the Michelson-Morley and similar experiments of that period are even nowadays difficult experiments of which no great accuracy can be obtained. 1967, he was saying how hard it was. Herman Bondi, a very well-known physicist. But strangely enough, this has no effect. Even a physicist writing this has no effect on textbooks which came later. The myth of the salience, decisiveness, and the sort of effortlessness of the Michelson-Morley experiment is still maintained. And the same goes for books which are written for a more general audience. Here, this book was written by a very famous scientist. You may have heard of him. His name is Albert Einstein. In 1938, he said, in view of the small time differences following from the theory, very ingenious experimental arrangements have to be thought out. This was done in the famous Michelson-Morley experiment. The result was a verdict of death to the theory of a calm ether sea through which all matter moves. No dependence of the speed of light upon direction could be found. Every experiment has given the same negative result as the Michelson-Morley one and never revealed any dependence upon the direction of motion of the Earth. So this was 1938, just 5 years after Miller had written the paper saying he definitely found a positive ether drift, and 13 years after Miller received his prize from the American Association of Science. And if we come up to the present day, here's another well-known scientist, Stephen Hawking, who you may have heard of. 1988, he is writing In 1887, Albert Michelson and Edward Morley carried out a very careful experiment at the Case School for Applied Science in Cleveland. They compared the speed of light and direction of the Earth's motion with that of right angles to the Earth's motion. To their surprise, they found that they were exactly the same. So the true story of the Michelson-Morley experiment is very, very rarely told, and it's very difficult to get hold of this notion that what counts as the truth in science is a matter of time, the formation of consensus over 40 or 50 years. In fact, it's embedded in a whole pile of social processes. Now, I would say this work that I just talked about opened up the way, opened the thin end. In English we have an expression, the thin end of the wedge. The wedge is something shaped like, oh, I can't do this with my hand. Something you put up to hold the door open. You know, triangular shaped piece of metal. You push the thin end in, use it to split a tree trunk. Push the thin end in, the tree trunk begins to open up. This material I've been talking about is the thin end of the wedge. And now we get to the Sociology of Scientific Knowledge, or SSK, sometimes called, and this is the thicker end of the wedge. This is a picture of my book. I could have put several others up, but I'm a very conceited person, so I always put my book up. And this is the Sociology of Scientific Knowledge. And the object is to investigate more closely the social nature of scientific knowledge, to investigate more closely how scientists create truth, especially when there is disagreement. This is an important book too. David Bloor said we should look at truth and falsity as a symmetrical process. We should look at them both the same way. Traditionally, under wave one, if you wanted to see how scientific truth was made, you just looked at the equations and the theories and the experiments. If you wanted to see how somebody discovered something that turned out not to be true, you looked to see what the pathology was. You looked to see what was wrong with it. Bloor said you've got to look at them both the same way. The construction of truth and the construction of falsity are similar social processes. This was a paper he wrote in 73. And now I'm going to talk about a couple of papers I wrote in 74 and 75, where I looked at how truth is established through repeating experiments, and how the truth of the matter is socially constructed. These papers here, 74 and 75, were written up in this book, as well as in the papers this book, which was not published until 1985. So we start off with a piece of apparatus called the T laser, which stands for Transversely Excited Atmospheric Pressure Carbon Dioxide Laser. This is not a T laser. This is not a T laser. T laser isn't here, actually. No. There it is. Now you can just about see a perspex box, long perspex box, and you can see wires and you can see electrodes. Okay. And in 1971 and 2, I got interested in how this device had just been newly invented. It's an interesting device, a very, very, very powerful laser. And interesting because the New Scientist magazine first announced the making of this laser by talking about a laser in a plywood box. Plywood, my translator knows what plywood is. This was a very easy, in some ways a very easy laser to make because you didn't use high pressures or anything. You used atmospheric pressure. You used a cheap old gas, carbon dioxide. But still it was very, very difficult to make because of the arrangement of the electrodes of the electronics. And I decided to do a study on how people learned to make this laser. And I drew what we would call then a diffusion network. The device was invented in Canada. This is how it spread from laboratory origin to laboratory X to laboratory Z. These were the paths in which the knowledge changed to a laboratory in Scotland, and also directly to another British laboratory who then sent it off to these other British laboratories. So this is a diagram of who learned what from where, but things are much less straightforward than this. This laser, as I said, was not well understood. Some people managed to make one, but they didn't necessarily know how they made it. So here is a description of the craft aspect which is involved in making this laser work. First of all, we had rows of fins instead of pins, but this didn't work too well. We thought this might be because the field uniformity was too great, so we put a row of trigger wires near the fins to disturb the field uniformity. Then we started finding out things. It did improve the discharge, but there are always delays involved. It definitely worked differently to the rationale when we first made it. Even today, there is no clear idea about how to get this thing working properly. We're even now discovering things about how to control the performance of these devices which are unknown. I have 4 theories for how they work, which contradict each other. The crucial part in getting a device to operate is the mechanical arrangements and how you get the things all integrated together in the electrical characteristics of the mechanical structures. This is all the black art that goes into building radar transmitters. And I tried to work out who had learned to do it. One important thing to notice about this laser is it's produced a very, very powerful laser beam. People were interested. They thought that maybe they could shoot down aeroplanes with it. They never could, but this was the, people were excited about it. But the laser beam was so powerful that if you put, say, a block of concrete in the path of the laser beam, then smoke would start to come out of the concrete, just from the sheer heat of the laser beam. So we could tell whether somebody had one of these lasers working or not, because you could see whether it would make the concrete or something else smoke, produce smoke and flames. And it turns out, according to my study, that only those people who had personal contact with someone else, another successful laser builder, managed to build a working model. There were quite a few people who looked at the journal articles, the circuit diagrams, and the photographs even, and put a laser together, a T-laser together, but the laser just didn't work, and they couldn't make it work. And I found that the only people who could make it work, apart from the original man who invented it in America, were people who had spent time, had a personal relationship with somebody else who had a working model. Sorry, I've just said that. Even those who used the literature alone failed, though they built something that followed the circuit diagram. To make concrete smoke, one of the team had to spend time with people who could already do it. Now, later on, one could begin to understand why. In some respects, this was the case why you had to spend time. This is my very rough circuit diagram of a laser. That is the big perspex box you saw earlier on with the lady standing next to it. Here is the row of pins. Here are the 2 big electrodes. And you must have a 60 kilovolt electrical discharge across here. And this is the circuitry. My drawings are not very good. A few capacitors. And this particular capacitor here, the capacitor. You have capacitor, Portuguese, yeah? Okay, capacitor. This is a big capacitor responsible for the final discharge. And the thing about this capacitor, in those days when the laser was being built in the 1970s, it was a very big and heavy object. You imagine it as being something like almost the size of a car battery. A big, big thing. So if you're going to build one of these from the circuit diagram, the obvious thing you would do would be to put the big capacitor down on the bench. Now, years later, it was discovered, that if you put the capacitor down on the bench, the laser wouldn't work. Why not? It's a perfectly sensible place to put it. It follows the circuit diagram. But it turns out that if you wanted to make the laser work, the capacitor had to be sited just above the perspex cavity in an inverted position, supported by a very strong framework. Why was this? Because it turns out that the electrical lead from the capacitor to the top electrode, which is around here, this one, had to be very, very short. If the lead was too long, then the inductance of the lead would be too great. But nobody really knew that. They just happened to build the laser with the capacitor here, and it happened to work. If you put the capacitor here, it wouldn't work. Now, if you went to somebody else's laboratory and saw how they built it and came back and built the same model, you'd probably put the capacitor in the same place and it would probably work. Okay? But if you didn't go to somebody's laboratory and you just looked at the circuit diagram, then the laser wouldn't work. So that, and now remember, this that I've told you is only something that people learn to understand later. At the time, some people were making successful lasers and some people were making unsuccessful lasers. The importance of the length of the top lead was not known. It was just a kind of example of tradition of laser building being carried forward successfully through interpersonal contact. But this is an unusual example where we come later to know exactly what's involved. When something that was unspoken, an unspoken practice that was transferred became spoken about. But there are always many other things in the arrangements that people don't even know that they need to know. They just have to do it the right way. And this, of course, is why mostly when you do an experiment, it just doesn't work. Anybody who does experiments as their research experiments as part of their day, anybody who does any kind of experiments, even undergraduate experiments, knows that mostly your experiment doesn't work. You put the thing together, try and make it work, and it doesn't work. And then you fiddle around and you fiddle around and you fiddle around and eventually you get it to work. In the case of the laser builders, they couldn't make the concrete smoke, they fiddled around, they still couldn't make the concrete smoke, and eventually they went and spoke to somebody else who had a working laser, and if they were lucky, then they could make the laser work. This is what happens when you do experiments in the laboratory. This is what happens when you know what the outcome of the experiment is supposed to be. But now we're going to move to a more controversial area of science. This was a second case study, and this was all turns around this man here, who's called Joe Weber, who in the late 1960s and early 1970s was building pieces of apparatus that look like this. This is a gravitational wave detector. Gravitational waves are ripples in space-time which are produced when enormous cosmic catastrophes take place. Two black holes collide or two neutron stars collide. It sort of shakes up space-time. But the effects are very, very, very tiny. Anyway, in the late 1960s and early 1970s, Joe Weber, who built this resonant bar, a bar which would be affected by the passage of ripples in space-time, said he was discovering, he was seeing gravitational waves. This is more of a schematic diagram. Here is the aluminium bar. Here are the piezoelectric crystals glued to its surface. The whole thing is insulated and isolated with a vacuum chamber, isolated from the ground, and the output from these are read off on a chart recorder, and you make sure with control instruments that nothing else is happening at the same time. And then if you get some unexplained vibrations appearing on your chart recorder, you say, this could have been caused by a gravitational wave. This is what, this is a piece of the photograph, the actual output of Joe Weber's apparatus at the time, which I took from his laboratory. That was the vibrations of the crystal. And you're looking for something like this, which seems to be a very high peak, or this, unexplained events which could be due to gravitational waves. The method pioneered by Joe Weber was like this. Well, first of all, let me just point out a little problem. If we go back to this chart, you have to ask yourself, well, what is an event and what isn't an event? And then you see you have a little choice to make. If that is the output of the chart recorder, magnified a bit, if you decide that the threshold is line C, then you have lots of events. If you decide the threshold is line E, then you have fewer events. And if you decide the threshold is line A, then you only have 1, 2, 3.5 events. Okay? So the first thing you've got to do, the first difficulty in analysing this data is decide where you're going to put the threshold to count as an event. Then Joe Weber invented a very ingenious variation of the experiment because nobody believed him. So his first apparatus was here, built in the University of Maryland near Washington, and then he put a second apparatus in Chicago, about 1,000 miles apart. here is the output from this Maryland apparatus bar, and here is the output from the argon bar. And then you compare the outputs of the two bars, and you say, well, if there's a coincident peak between the two of them, the only thing you can think of that might have caused it would be a gravitational wave, because they're 1,000 miles apart. So there's a coincidence, and there's a second coincidence, and there's a third coincidence. So in this little time period of output from the two bars, you have three coincidences which are putatively three detections of gravitational waves. And then, this is the really clever stuff, to make sure that this isn't just noise, you could have a look and see how many of these events would be caused just by noise. And here, you take the output from the Maryland bar, and you offset it in time. So you slid it sideways in time. And then you look for coincidences between the offset output and the correct time from Maryland and the correct time output from argon. And here, if you trace it back forwards, I'll just do my little graphic again. You look, where's there's only one. So there is one coincident event between the offset one and the proper time one. How many coincidence events, how many of these events could be caused by gravity? None. Any event, any coincidence between an offset output and the correct time output can only be due to chance. And by putting more and more offset outputs, you can build up your knowledge of how many outputs could be due to chance, and then you can look to say, well, in the real time, are there more outputs than there are in all these chancy ones? And you produce what's called a delay histogram. Here's a couple of examples from Joe Weber's work. This one is, both of these are from 1973, actually, different times of year. And you see, at zero delay, when the two timings are correct, there's 566 events, whereas in the background, with the time slides, 90 seconds, 60 seconds, 30 seconds, 20 seconds offset and so on, there are far fewer. So that's the background noise, and these are the genuine signals between there and there. Likewise on this, not quite so clean, but you see the same sort of effect. And this was his experimental result. Anyway, people didn't really believe Joe Weber, because by calculating the sensitivity of the apparatus, and by calculating the theory of gravitational waves, they reckoned he was seeing 1,000 million times too much gravitational wave energy. And so he was the most he became for a while the most famous scientist in the world, but few people believed him, and an awful lot of people didn't believe him. In 1969 he was saying, this is good evidence that gravitational wave radiation has been discovered. Then, one of his assistants, later in 1969, wrote to other people, a number of you inspired by inspired, it says inspired, maybe the word should be annoyed. Some people it was annoyed, some people inspired. A number of you inspired by the recent publications of Professor Joseph Weber at the University of Maryland concerning the possible detection of gravitational radiation have written letters to me requesting information on the techniques for constructing gravitational wave antennas. Since it is essential that we learn more about the events that Professor Weber has detected, and the best way would be to have independent groups study them, I would like to take this opportunity to make the same offer to you that I've made to those who have contacted me. If you think you can obtain the funds necessary for the purchase of the equipment, I will be willing to take time from my projects to supply technical advice and assistance during the critical phases of your work. And in fact, about half a dozen other groups decided to test Joe Weber's findings. But think about the T-laser for a moment. How could you tell whether a gravitational wave detector was working? In the case of the T-laser, you knew whether the T-laser was working or not because it could make concrete smoke when it was working, and everybody knew how long to carry on, how hard to try. But what is a working gravitational wave detector supposed to do? Is it supposed to see gravitational waves? A working gravitational wave detector of Joe Weber's design? Is it supposed to see gravitational waves? Or is it supposed not to see gravitational waves? Nobody knows. So how do you know when your gravitational wave detector is working? And so the arguments about whose experiments are good ones can go on forever. In the case of the T-laser, the arguments came to a stop, because if you couldn't make your concrete smoke, then you didn't have a T-laser that was any good. But in the case of gravitational wave detectors, what is there to tell you whether the apparatus is working or not? And in fact, this is what happened. So I'm now going to describe a series of experiments. Experiment 1 was described to me by a scientist as a pretty good experiment. The W experiment, though it is very complicated, has certain attributes so that if they're seeing something, it's a little bit more believable. But the same experiment was described by another scientist as not very good. They hope to get very high sensitivity, but I don't believe them, frankly. And a third scientist said of the same experiment it was rubbish. The group at W are just out of their minds. So you see, so how do you get consensus when people have completely different views about the same experiments? And we can go on and see the same thing for experiment 2, a different experiment, competing with Joe Webber. He's at a small place, but I've looked at his data and it certainly is interesting. I'm not really impressed with the experimental capabilities, so I question anything he has done. That experiment is a bunch of shit. And the third experiment, their result seems quite impressive. They're very businesslike and not quite authoritative. My best estimate of his sensitivity, and he and I are good friends, is low. He's just got no chance of detecting the gravity waves. If you do what they have done and just give your data to some girls and ask them to work that out, then you don't know anything. And the final one, experiment 4. Their experiment is quite interesting and shouldn't be ruled out just because they can't repeat it. I'm very unimpressed with their experiment. Now that experiment is just an out-and-out fraud. So you see you have different opinions about the same experiment, and these different opinions can be maintained and carry on and are very, very difficult to settle because you've got no clear criterion of when the experiment's working. Some of these experiments will be seeing gravity waves, some of them won't be. And this leads you to what we termed in a 1985 book, The Experimenter's Regress. To know whether an experiment has been done competently, you must check to see if it produces the right result, just like the T-laser. But to know what is the right result, you must do a competent experiment. But to know whether the experiment is competent, you must know the right result, and so on and so on and so on and so on and so on. So it never becomes settled. And this is how the controversy over gravitational wave experiments tended to go. If you believe high flux, this word here means a lot of gravitational waves, which means that an apparatus like Joe Webber's, which is 1,000 million times too insensitive to see the waves according to the theory, but if you believe that he's made the discovery that there really are high quantities, high fluxes, 1,000 million times as much as anyone thinks, if you believe that high fluxes of gravity waves can be detected these days, if you believe that, and you're talking about a claim to have detected high fluxes of gravity waves, somebody says they've seen them, then you're likely to say that experiment is a competent experiment. But of the same experiment, if you don't believe that high fluxes of gravitational waves can be detected, you're likely to say it's an incompetent experiment. Then if we go to a different experiment which claims not to have seen high fluxes of gravitational waves, and you believe in high fluxes of gravity waves, then you're going to say that's an incompetent experiment. But if you don't believe in gravitational waves, you'll say, hey, they've done that really well. There are none to be seen, and they haven't seen it. So that's how the arguments over the experiments pan out in the case of gravitational wave detection, and you can generalize this for any controversial phenomenon. And here we come back to go back, this is an illustration then of how the Wittgensteinian or the Winchian position of the combination of conceptual life and practical life go together. You make your decision about which experiments are being done properly, and you make your decision about what is the truth of the existence of gravitational waves, or whatever phenomenon you're interested in, you make the decision at the same time. You decide then how your social life is to go forward, with this set of practices, or with that set of practices, with this set of beliefs and concepts, or with that set of beliefs and concepts. So the whole thing is a social change, just like a paradigm change. And you can see from the previous description of the gravitational wave controversy how one can put flesh on the bones of the idea of paradigm revolution. But the old model of science, where things were not as complicated as that, it was just a straightforward matter like the Michelson-Morley experiment of doing an experiment which took no time, was maintained by inventing and writing about mythical histories of science of the sort we saw in the textbooks. It was maintained by concentrating on cases where consensus was already well established rather than actually being established. It was maintained by taking Newtonian or Einsteinian physics as the quintessential cases, but actually Newtonian or Einsteinian physics are very, very, very simple pieces of science. Yes, the equations are complicated, but there's not much going on in space. Planets are just moving around stars without much interfering with their movement. There's no real complexity there. Compare, for instance, space physics with weather forecasting, or global warming, or economics, where there's so many complicated things going on that you don't expect clear, clean answers. And yet, the danger is that the public has been led to expect clear, clean answers because of all these processes that have been going on. So if you compare Newtonian science with anything that is complicated, chaotic, or deeply controversial, you'll find that they're very, very different sorts of processes. So as for theory, observation and experiment, even the best of science doesn't take you far away from ordinary reasoning and ordinary prejudice. It does not provide a sure escape from the essential angst that I mentioned at the beginning. And even if you don't believe anything I've said about physics, it's still true for the difficult sciences, and it's still true for controversies over the short term, even if experiments can settle them in the long term. And that's a point that I really want to emphasize. You don't have to believe anything I've said about the deep nature of science, still to have to believe it's true for controversies in the short term, or for anything that's really complicated and complex. I want to emphasize that point, emphasize it, and emphasize it again, really emphasize it. Now we move on to wave 3. That's wave 2. Wave 2 says it's difficult, it's very hard to see how an experiment, a theory, or an observation will settle something in a really complicated and controversial area. It's difficult to see how the science is going to step in and give you these universal truths that we all want. In any case, the speed of politics is further than the speed of science. If some great big political decision rested on the outcome of the Michelson-Morley experiment, well, you'd have to wait 50 years to find out whether it was true or not. And politics goes faster than that. Nevertheless, if we want to preserve our civilization as we know it, then we still have to take science and technology and these things as contributing in some special way to the technical decisions that are made in the public domain. We've got to give special weight to the opinions of people who know what they're talking about when compared to people who don't know what they're talking about. Otherwise, our society will become chaotic. For example, if we don't give special weight to people who know what they're talking about, you could have saved the trouble of flying me over from Britain and brought in anybody from the street to give this talk. Now, you may say that might have been better, but for those of you who don't think it's better, then you've already agreed with me that in order to preserve some semblance of sanity in society, you have to give special weight to people who know what they're talking about. Okay? And this presents a philosophical problem, since everything we've said about wave 2. How to resolve this problem. And this is what wave 3 is intended to do, to try to resolve this philosophical problem. If you can't resolve the problem, we're stuck without being able to give answers to questions. And one of the reasons I got into this, I remember coming back from the History of Science conference, and was on the bus to the airport with some South African anthropologists who said to me, well, all this wave 2, all this relativism and so on that you talk about is very fine, but what am I supposed to do with it when I go back to the South African townships and I find that men believe that the way to cure their AIDS is to have sex with a virgin? What am I supposed to say? You may be right, or am I supposed to do something about it? And what tools can you provide to do anything about it? And I didn't know what the answer was. Or what are you supposed to say to the parents of children in Britain who for a long time were convinced that the mumps, measles and rubella vaccine would induce autism in their children? And they were convinced of this, even though there's absolutely no scientific evidence for it whatsoever. Yet they were ceasing to vaccinate their children and producing a measles epidemic, which was beginning to do serious damage. And doing especially serious damage to children who are too ill to have a measles vaccination. What do you say? You must have to find something else to say. Well, because wave 2 doesn't offer any answers, doesn't tell you what to say next. So our move was to move away from talking about truth to talking about expertise. The problem of truth is really insoluble. Expertise is a more soluble problem. Politics is faster than science, but politics isn't necessarily faster than expertise. The reason is the judgments of science are very, very slow because science aims at certainty. You can never quite get it, as wave 2 shows, but that's what it's looking for, certainty. It takes a long time, 50 years for a typical scientific controversy. Politics can't wait that long. But expertise, or estimations of the nature of expertise, can move fast. Because when you're looking for expertise, when you're looking at expertise or trying to assess expertise, you're not looking for certainty, you're just looking for the best that you can do. You know that the outcome may be wrong. You know that it can be fallible. But you're saying, may be fallible. But you've got to make some decision. And surely when you're making some decision, you should just give a bit more weight to people who have expertise, people who know what they're talking about. And this leads to a new program of research. The study of the nature, ownership and applications of expertise, which Rob Evans and I have been doing since the turn of the century. The beginning of this program of research is a classification of types of expertises. And this classification is called the periodic table of expertises. I told you I was a very conceited person, so we call it the periodic table of expertises. And that is for tomorrow. Thank you.
Nós estamos agora abertos a perguntas da plateia. Qualquer pessoa que quiser colocar alguma questão para o professor Henry Collins, por favor, levante a mão e olhar aqui comigo.
Bom dia, professor. Parabéns pela sua palestra. Meu nome é Daniel. Eu, na verdade, sou um estudante livre ainda. Estou ainda me descobrindo no campo da história e da filosofia da ciência e agora da sociologia. Eu queria que o senhor falasse um pouquinho mais sobre... o Thomas Kuhn ele faz uma crítica ao seu trabalho no Caminho desde a Estrutura, em que ele tenta rever os conceitos, principalmente de incomensurabilidade e de revolução dos paradigmas. E cria ali o conceito de léxico, ele se aproxima um pouco, eu acho, do Wittgenstein com o conceito de gramática do Wittgenstein, o conceito de léxico do Thomas Kuhn, e o senhor disse que ele não deveria ter feito essa revisão, que ele estava certo, que as evoluções existem e que há mesmo incomensurabilidade, e ao mesmo tempo elogiou a leitura, o trabalho do Wittgenstein. Então eu queria que o senhor explicasse um pouquinho melhor essa colocação, em que me parece que Thomas Kuhn se aproxima do Wittgenstein, e o senhor elogia o Wittgenstein, mas ao mesmo tempo diz que talvez essa aproximação não deveria ter acontecido. Obrigado.
So, let me see if I understand your question. You want me to say a little bit more about the relationship between Wittgenstein and Kuhn? See? Well, I will tell you a personal story. That in fact I was once at a conference with Thomas Kuhn, who was giving a talk, and at the end of this conference I put up my hand and said, well, you should read Peter Winch's book and you would understand your own book better. And I went to the front of the stage and explained exactly what I've explained here, that really the notion of paradigm is just the Wittgensteinian notion of form of life, but applied to science. And I said, Peter Winch has already said everything you said about this. Some 4 years before, he took it from Wittgenstein. And Kuhn was not so happy about this. But he said it was an interesting point. I think my friend Trevor Pinch has written a useful paper on Kuhn, which makes this point and expands it a bit more. That there is a strong early Kuhn and a weak later Kuhn. And the weak later Kuhn is making a mistake because he really doesn't understand the Wittgensteinian philosophy deeply enough. And I know from this conference, when I talked to Kuhn about this, that Wittgenstein was not as big an influence on his thinking as it should have been, given what he was doing. So I would say, if you're studying these things, you could make some progress by looking at Trevor Pinch's paper, and maybe you could impress your tutors by criticizing Kuhn, pointing out where he went wrong.
The act of scrubbing reinforces the mind. Oh, there is germs and I'm getting rid of this. Of course, I'm totally cool with that. But maybe if you could explain better, because there are germs and anything that no committee of infection of the hospital will statistically prove that the infection rate goes down if you scrub your hands. So I was kind of annoyed about it.
There are very many different levels at which you can understand this point. Now, first of all, I believe, maybe you can confirm this, that if you look at an operating theatre, you will see that different people in the operating theatre take different amounts of care over the hygiene. Maybe sometimes the top surgeon will not always have the mask across his face, whereas all the nurses will. So there's different, slightly social conceptions of germs. Secondly, at a very, let's say, a deep philosophical level, there were no germs before they were invented. You could go when people were operating with bloody waistcoats, and in that world, there were no germs. You know, nobody could have the concept of germ then until somebody invented the concept of germ. Thirdly, the statistical experiments. I cannot disagree with you about there being germs. When I cut my finger, I put on some disinfectant because I believe in germs. I cannot not believe in germs, but then maybe I'm just in this society which forces me to believe in germs. Just as it, like I said at the beginning, it forces me to believe in other things. For instance, I do not believe that English is a superior language to Portuguese. But now I'm going to try an experiment. I'm going to try to speak in Portuguese to show how relative these things are. Won't come out. So in the same way that I don't have the choice to suddenly start speaking in Portuguese, I don't have the choice to suddenly start not believing in germs. So all the experiments and the statistics that you quote to me, of course I accept them. So an interesting thing is that I've never done one of these experiments. Have you done one of these experiments? You've only read about them. So you just believe what people tell you. What sort of a scientist are you? You just believe what people tell you. And you come here and you say you must be wrong because somebody told me you're wrong. Here is sociology at work.
Professor, o senhor falou a questão da AIDS, da vacina na Inglaterra, e há uns meses atrás o sociólogo Reitoria esteve nesse mesmo auditório falando da importância da gente dialogar com outros tipos de saberes, né? E da gente procurar não hierarquizar esses saberes, colocar um saber acima do outro, e que se a gente, nas ciências sociais, conseguir promover um diálogo efetivo entre esses saberes, toda a ciência, toda a sociedade, toda a humanidade tem mais a ganhar. Eu queria saber um pouco da sua opinião a respeito disso.
This is a very important question. Because nowadays there is a very strong movement in the social sciences of the kind that you describe, which is all about dialogue and taking everybody's point of view into account and so on and so forth. But really it solves no problems. Of course, you should understand everybody's point of view. Understand it. This is a basic feature of the sociologist's work, especially somebody who is like me. I would call myself an interpretative sociologist. And the interpretative sociologist must always begin by trying to get inside the world of the actors. And so in this case of, say, MMR, mumps, measles and rubella vaccine, their anthropologists have done studies of what was inside the minds of the parents of the children who did not want to give their children the vaccine because they were afraid it would cause autism. And the most plausible, acceptable explanation of what they were thinking was that, well, maybe the epidemiological studies have shown that there is no harmful effect of the vaccine, but maybe my child is especially susceptible, okay? And the epidemiological studies cannot show that's not the case. So maybe these parents wanted a special study to see whether some particular children might be specially susceptible to MMR. Now many sociologists think that's the solution, the way to go. You should give these parents what they want. But how did these parents come to start to believe that their child was, that anybody would be susceptible to autism by being given an MMR vaccination? Then you look at where it started. It started with a doctor called Andrew Wakefield, who said this at a press conference, with no evidence at all. Many people believe that he said it in an article in The Lancet. And the editor of The Lancet has apologised for publishing this article. But if you read the article, he did not say it in the article. What he said in the article is he's found some correlation with 6 children of measles virus in the gut and autism. Okay? But then he said you should still vaccinate your children with measles vaccine. Just give it single vaccine. Okay? So why was he saying this if he found something about measles virus in the gut and autism? He just said at the press conference, maybe the cause of this is MMR. And then newspapers pick it up and everybody think MMR, MMR, MMR. There is no evidence for it. So supposing I were to get up tomorrow morning and say, listen, you know what causes autism? Eating kiwi fruits. You have kiwi fruits in Portugal? Okay, no evidence. Then the newspapers pick it up. Hey, and parents could say, hey, maybe my children are. Maybe the epidemiological evidence doesn't show too much, but maybe my particular child would get autism from eating a kiwi fruit. I demand a scientific investigation of whether it's kiwi fruits. Now you see you can ask for that for any number of possibilities. And if you ask for any number of possibilities, then you spend all your money for medicine on this huge range of possibilities to satisfy a few middle-class parents. Okay? Meanwhile, children are dying of measles, and meanwhile children are dying of other diseases because the resources don't go into it. So somehow you have to make the decision on some other criterion than necessarily the actor's perspective. Now the same goes for this AIDS in South Africa case. You can understand why men in South Africa think that having sex with a virgin will get rid of their, or cure their AIDS. Easy to understand, because the theory of disease causation in the South African townships is all to do with dirt, not germs, but dirt. And they think that a virgin is somehow clean, and the cleanliness of the virgin will somehow remove the dirt from them, and then they will be better. So there is the perspective of the actor. So what do you do? You say, oh, that's the perspective of the actor, finish. Of course you don't. And the idea that all you have to do is take the perspective of the actor to solve any problem is nonsensical. This is a really difficult thing, because somehow or other you still, if you want to preserve the sort of society we have, if you want to believe that sex with a virgin does not cure AIDS, you have to make this hard decision to say, hey, I too have some expertise and it's better than your expertise. For a social scientist, that is one of the hardest things to say and the hardest thing to work out how to say. Nevertheless, there is no choice but to do it. I could give you many more examples if you want.
My name is Thiago. I'm graduating myself in philosophy of science, and I'd like to thank you for your lecture. I think I have a lot of stuff to think about now. But my question is, I think it's a naive question, but you said that Newtonian physics is a very simple science, okay? But I think as a philosopher, and I still may say, okay, these chaotical science are still chaotical. So, still chaotical. These chaotical. Sorry.
Yeah.
These chaotical science are still chaotical science. So they don't obey, they don't follow a rational pattern yet. But in the future, maybe. I think this is this maybe is some kind of faith in determinism, and this kind of things. But I think we still have arguments to defend this kind of position. I'd like you to say just a little bit about this thing.
The third wave, I completely agree with you. In fact, in our book, Rethinking Expertise, we even defend econometric modelers. And we know, because my colleague Rob Evans wrote a whole book about econometric modelers, that the science of predicting the future of economies is completely hopeless. Never gets it right, always gets it wrong. But we still defend econometric modelers as experts, and we say we still have to keep them, because maybe one day they will be able to do something a bit better. The argument actually comes from the philosopher Nelson Goodman. Nelson Goodman wrote a book called Languages of Art. And in this book, Languages of Art, he asks the question, why are we concerned with the difference between good art forgeries and the genuine article? Never mind the value and all that kind of stuff. But what, if you can't tell the difference between a forgery and the real thing, why are you concerned with it as a piece of art? And the answer Nelson Goodman gives is this, that learning to observe is something that you learn over a long period of time. And maybe in the future, you will learn to see the difference between the genuine and the forgery. But if you don't establish the difference between the genuine and the forgery, then you'll never learn to see it. So yes, I completely agree that we want to preserve expertise, but if I go back to being a wave 2 person, well, the chaotic sciences, the weather forecasting, maybe sometime in the future, maybe, maybe not, who knows. But for wave 3, of course, it presents typical problem that you have to, policy problems come in the short term, not in the long term.
Meu nome é Bernardo, eu sou da Faculdade de Educação. Eu queria perguntar sobre a terceira onda. A primeira questão, são duas questões pequenas. A primeira delas é até que ponto essa ênfase sobre expertise consegue deixar de lado a questão da verdade ou a maneira como a filosofia tratava essa questão, se a posse da verdade ainda não deixa de ser um grande peso no mercado de crenças ou na autoridade que o especialista tem hoje em dia. E a segunda, em relação à terceira onda, é se essa abordagem, primeiro caracterizando como uma onda, não é só, seria para além do trabalho que vocês fazem lá, outros, você vê em outros sociólogos da ciência, também se movendo um pouco para uma indagação sobre as implicações do relativismo e uma mudança na sociologia da ciência, com base nas implicações que ela traz e não tanto mais na denúncia, enfim, está mais preocupada com as implicações sociais que a sociologia do conhecimento traria. Se você vê isso como uma onda e também em outros lugares, são essas duas questões.
So the first question is whether the
o peso,
concentration on expertise can eliminate the worry about truth.
Yes.
And the answer is no. But I think now we have been, philosophers, sociologists, particularly philosophers, have been trying to establish the grounds of truth forever, and nobody can do it. Nobody can do it. And the biggest danger of this is, I mean, you know, it's, in some sense it's not such a real danger. Let me put it this way, when David Hume invented the problem of induction, the world didn't collapse. Now, as far as I know, there is no solution to the problem of induction. We really don't know that when we walk out of that door after this lecture, we won't fall into a fiery pit full of dragons. But we don't actually worry about it too much. And I think, in a sense, what has been taken to be the policy implications of wave 2 are a little like saying there's real policy implications for the problem of induction, because we never know what to do next. It doesn't follow. It doesn't follow. There is still order in the world. But you can still have order in the world without solving the problem of the foundations of truth. And for policy purposes, because really the policy problem only becomes difficult and dangerous when there is dispute, so there is no established truth. And here I do think that the expertise approach does valuable work. Now, do I see it elsewhere in the general field of sociology? I don't know. And in our own field, science and technology studies, we find a huge resistance to what we're doing. We are fighting a battle to make it established. And we are slowly winning this battle. We are now, the things we talk about get published, at least, if not always with great pleasure with the mainstream journals like Social Studies of Science. They do get published and discussed in Nature, in American Scientist, even, believe it or not, this Friday, in Scientific American online, some of this stuff will be discussed. So we think it just makes sense, and it will eventually win the day because it's the right position, and if we have to lose some colleagues along the way, well, maybe this is the, as we say in English, the badge of honor, that you have some enemies.
Muito obrigado pela presença, pela palestra. Me parece assim que ela traz uma ansiedade natural e também uma busca de um ponto. Quer dizer, essa busca de um ponto que é controversa é o que também gera assim curiosidade, e essa busca contínua na humanidade, em mim. Não interessa se é brasileiro, se é inglês, se é africano, né? Então eu só quero discutir assim um pouco quais os critérios de discernimento diante desse caos, que parece que há uma inteligibilidade, algo que vai norteando, que vai orientando a vida de um sociólogo que é cientista e que faz, através desses experimentos pontuais, assim, que a ciência progrida. Então a minha questão é, nessa vida de cientista,
que tens, que construiu durante essa trajetória, essa história, quais seriam os... Eu reluto em usar referências, mas quais seriam, assim, alguns critérios que nortearam o caos?
So this comes to, again, a sociological question, that in fact, it is not the case that every standard requires a philosophical foundation. So, for example, let me say I meet somebody in a pub, in a bar, who sits down to have a discussion with me. And this person says to me, look, I am not sure whether it is wrong to torture children for no reason. Can you prove to me that it is wrong to torture children for no reason? If you cannot prove it to me, then I don't know that it's wrong. I'm going to go and torture some children. At this point, I believe you have to say, sometimes searching for a justification is the wrong thing to do. In these circumstances, what you should do is call the police. And the same thing goes for the standards of myself as an academic. I believe as an academic, as somebody who works at a university, then my life must be, to make sense of my life, I must search for the truth. That is what I think I do. I search for the truth. Now the fact that I can also show that searching for the truth may not have any good philosophical foundations, it's too bad.
Bom dia, obrigada pela conferência. Eu sou Patrícia Galarque, professora do Departamento de Filosofia aqui da Universidade. A minha questão é relativa a... Eu gostaria de entender melhor a passagem da segunda onda para a terceira onda. A passagem da primeira para a segunda é muito nítida, né? Onde você tem um programa de uma espécie de busca por uma teoria científica que corresponda mais à realidade, para a segunda onda em que você tem que as teorias científicas são socialmente determinadas. O que me escapa um pouco é essa passagem da segunda para a terceira, né? Na segunda onda nós temos, né, Thomas Kuhn como grande representante, que já colocava no seu conceito de paradigma, por exemplo, a determinação a partir das organizações da comunidade científica, onde as políticas do incentivo eram determinadoras dos padrões de racionalidade e de pesquisa. Então, o que eu gostaria de entender é o que a gente ganha e o que diferencia a passagem da segunda para a terceira onda, e o que a gente ganha com a substituição, por exemplo, do conceito de paradigma pelo conceito de expertise.
Yeah, this is a good question and something I should have made more clear. In some respects, this language, wave 1, wave 2, wave 3, is misleading, because it is certainly the case that wave 2 replaced wave 1. But wave 3 does not replace wave 2. Wave 2 continues. So I still do this work. I'm still studying gravitational waves, and I hope in a few years, when gravitational waves are finally discovered, 50, 60 years on from when somebody first said they discovered them, I will write another book. I've already written one book about this gravitational wave business, by the way. It's 875 pages long. So I'll write another book, thinner, which will be about how finally the existence of gravitational waves wasn't socially constructed. But wave 3 is meant to ask a different question. It doesn't ask how is truth constructed or how is truth made. It asks the question, what shall I do next when truth hasn't been constructed? It's a different kind of question, and it has a different kind of answer. So the two things, the wave 3, there is not really a transition. This is my fault. There's not really a transition from wave 2 to wave 3. There is an addition of wave 3 on top of wave 2 and says, now given that wave 2 is already running and stays running and doesn't reduce, how do you answer these other kinds of questions about what the policymaker does, and how do you answer it in such a way that you don't simply say the only answer is democracy, everybody should have an equal say in the matter, because that isn't going to work. That will produce disaster. Somehow or other you have to answer it in a way that still gives some weight to science and technology and people who understand and know what they're talking about, in spite of the fact that wave 2 is still running. And so, different kind of answer, I find, maybe Rob Evans will put it up on his talk, but in the last chapter in appendices to our book, Rethinking Expertise, we have a lot of explanation about what is the exact relationship between wave 1 and wave 2, what is the same, what's different, and so forth. But it's my fault for talking in waves as though one just washed away the other. Wave 2 washes away wave 1, but wave 3 does not wash away wave 2.
Bom dia, professor. Obrigada pela palestra. Meu nome é Ruth Schmitz. Eu sou aluna do programa de pós-graduação do doutorado aqui da Faculdade de Educação e trabalho com educação em ciências. Minha formação primeira é em física e tem uma trajetória que me levou a investigar um problema que é exatamente lida com a questão de como que o conhecimento técnico científico, ou seja, o conhecimento daqueles que sabem o que estão falando, né, comparece nas escolhas coletivas, nas escolhas políticas feitas de modo coletivo. A afirmação que o senhor nos trouxe aqui, de que temos que dar um peso especial à opinião das pessoas que sabem o que estão falando, de certa forma me aponta para uma resposta, né? Quer dizer, esse conhecimento científico, de certa forma, ele não comparece como deveria, né, ou como a gente espera que comparecesse, né, nessas escolhas. A minha pergunta é, como implementar esse propósito de dar um peso especial à opinião dos que sabem o que estão falando, e quem vai decidir quem é que sabe o que está falando?
This is tomorrow's talk. Of course, it's a very, very difficult problem. There's a number of misconceptions about this program. The first thing is that, and it's very important to remember this, that even people who know what they're talking about disagree violently with each other. And all we are saying is you must let those people, if you want to know people who know what they're doing, bring them in, allow them into the argument with special weight to what they think, even if they disagree with each other. But there can be other people who disagree or agree, but they don't belong in, because they don't know what they're talking about. So the demarcation criteria is to have people who know what they're talking about separated from people who don't know what they're talking about. Now this, as you intimate, is difficult. What is the thing that is being talked about? Is one interesting question. How do you do the demarcation? It's very, very difficult. And we proceed, I suppose, in 2 or 3 ways. The first thing is we try to classify all the different ways of knowing what you are talking about. And this is the periodic table of expertises, which I will start with tomorrow. Okay. The second way is we take case studies and show where it goes wrong. So the MMR case study is one of these. It went wrong because people who were basing their views on somebody who didn't know what they were talking about, taking their ideas from somebody. The same, one of our graduate students has done a marvellous study of Thabo and Becky, decision not to distribute antiretroviral drugs to pregnant mothers in South Africa. An orthodox medical opinion would say that as a result, tens of thousands of babies in South Africa have acquired AIDS because Thabo and Becky did not believe in the efficacy of the drugs. One of our graduate students has pointed out that Thabo and Becky didn't know what he was talking about either. And it's a very exact meaning doesn't know what he was talking about. The reason he didn't know what he was talking about, and I'll talk about this more tomorrow, was because he got his information from the internet, which is not a reliable source of information. And you can say that if he wanted to know what he was talking about, he should have gone and talked to scientists and spent some time with the scientists themselves, not just taking it from the internet. So this is another case study that shows where it doesn't work. And thirdly, there are people who are tremendously highly qualified, highly skilled experts in areas like astrology or intelligent design or something like this. They're experts. So how do we push those out? That's again difficult. It depends on a rather old-fashioned philosophical approach to do with trying to recreate demarcation criteria between science and non-science. And somewhere along the line, I guess we should try and talk about how we try to do that. But again, it's a social criteria. Who is trying to make contact with the existing scientific community? One thing I should say is this program, this Wave 3, like I said, this has very, very shallow philosophical roots, not deep philosophical roots. It all starts from the preference of wanting describe tomorrow. Maybe they're not right. But there's nothing wrong about the program. It's just what I choose. If you don't choose it, you don't have to choose it. If you want to live in a society where you would bring somebody in off the street to give this talk instead of me, well, you're entitled to do it.
Professor, meu nome é João Martins, Departamento de Engenharia de Produção. Eu sou amador, né? Ao ler esses assuntos, eu sou amador, mas eu gostaria de saber o seguinte. Nessa postura do mundo relativo, né, e de que nós estamos sempre buscando a verdade que foge de nós, como cientistas, eu acho razoável afirmar que o absoluto, a verdade absoluta não existe? Ou, melhor dizendo, aceito a minha ignorância como cientista, ponto final?
No, I think you are in the same position as me. When I answered the question up there, from the person up there, how do I justify my seeking after truth? Well, that's the most efficient way to live my academic life, is to believe that I am seeking the truth and finding the truth, and even if people won't believe it now, they will believe it eventually. And I believe this is the right attitude for scientists when they are working at the bench. They must believe they are trying to find the truth. When the scientist goes into the wider world and becomes a citizen and talks about the meaning of their science for citizens, at that point a more nuanced, is this a Portuguese word? Nuanced? Yeah, a more nuanced approach is necessary, perhaps from sociology. But for doing the day-to-day work of science, the best way to carry you forward is to believe you are seeking the truth. It's like an athlete. If you go in for a race not believing you will win, then you will lose. So you have to believe you will win.
Professor, o meu nome é Rafael, eu sou estudante de pós-graduação da Universidade Estadual de Campinas, no Programa de Política Científica e Tecnológica. E alguma coisa me chamou a atenção na sua exposição. Você estava demonstrando o papel das controvérsias do desenvolvimento científico e tudo mais, e daí me chamou a atenção no seguinte sentido. Como seria, assim, tentando aplicar essa mesma fórmula de estudos de ciência e tecnologia para o próprio campo? Primeiro, o que iria conduzir esses estudos sobre controvérsias científicas dentro do campo de estudos sociais da ciência e tecnologia, e outro, quais seriam as possíveis descobertas advindas desses estudos? Muito obrigado.
Okay, so this has been done by a man called Malcolm Ashmore, who wrote a book called The Reflexive Thesis, which is actually quite amusing and very funny. One of his people he studies is me. I think he makes a few mistakes, but on the whole it's an interesting book. But it's one of these things that it's been done. And now it's been done, the best thing to do with it is forget it. Never think about it again. It's not the case that the whole world is consistent. To make the world, what is people are not sufficiently sociological. The sociologist thinks that what moves forward is social understanding of society. The people who think it's absolutely necessary always to be self-consistent are thinking that the individual has the responsibility for all knowledge. Now, the individual has responsibility for doing the best they can do in what they are doing. That is why this gentleman over here should seek the truth and I should seek the truth, and we don't have to worry about whether the truth, at the same time we're saying this truth is something rather strange that you can't obtain. Do your best. It will all turn out in 50 years' time, when history has settled who's right, who's wrong, how it all adds up together. But if you want to read about how this can be done, Malcolm Ashmore's book, The Reflexive Thesis, is quite an amusing thing. Such a book should never be written again. But it's good that it was written once.
Eu agradeço mais uma vez a sua excelente apresentação.